me recall first the end of the last lecture. I almost proved the following theorem. You take the integral over Rn and then the exponent is a quadratic term plus minus minus 1 over n factorial, and then sum over I1 In, b I1 In, x I1 x In. dx. So it's a formal power series in x, and again, the integral is understood as the principal value or as the limit as epsilon goes to 0 of this integral with the suppressing exponential factor, suppressing Gaussian exponential factor. And the statement is that this is equal to 2 pi to the n over 2 e to the I pi over 4, the signature of B. These are the Gaussian contributions. This is what we would have if all these would be 0. But then the next contribution is sum over non-empty 1 plus sum over non-empty graphs IH to the power of minus the Euler characteristic of the graph divided by the number of automorphisms of gamma, and then the weight of the graph gamma. So here there's the number of vertices minus the number of edges, and so the proof is very straightforward. You just expand in h this exponent, and we did most of it last time. So we ended up with the formula, if we call this integral I. We ended up with the following formula for I. It's this Gaussian prefactors e to the I pi over 4, the signature of P, then the determinant of P, the absolute value, and then sum over n3, n4, n5, and so on, greater or equal than 0. I to the power n3 plus n4 plus and so on. H to the power 3 over 2 minus 1 and 3 plus 4 over 2 minus 1 and 4 plus and so on. Divided over n3 factorial, 3 factorial to the power n3, 4 factorial to the power n4, and 4 factorial, and so on. And then there is always a struggle with pluses and minuses in this formula. So since I put here minus, I assume I should put it here as well. Well, let's put it there and let's see what will happen. So so then it's the sum over perfect matchings, and then f, the weight of the following graph. So here you have the perfect matching on well, on the set of these points. Then you connect here trivalent vertices, and 3 of them, 4 valent vertices, and 4 of them, and then so it's the sum of all these finite collections of non-negative numbers. In each collection there is a last one, so there's nk of those. And then the weight is computed in such a way that, so f is computed in 2 steps. First you assign indices I1, I2, I3, and so on to this point. These indices, they go from 1 to n. Then to each arc, ij, you assign b inverse ij, and then to each vertex, I1, I2, Ik, you assign the weight b, I1, Ik. And then take the product of weights, take sum over all i's, product over edges, the weight of the edge, and then product of vertices, the weight of the vertex, and the weight, this is the weight of the edge, and this is the weight of the vertex. So as a result, let's look at the numbers. So as a result, this sum over perfect matchings, this summation becomes sum over all graphs with n3 trivalent vertices, n4 4-valent vertices, n5 5-valent vertices. Then the number of perfect matchings, the number of m producing this graph, and then the weight of the graph. Is this clear? Because you see what can happen is some of the perfect matchings will give the same graphs. Let me give you some examples. So let's look at three. This is the simplest example. So you have perfect matching like this. You have perfect matching like this. You have perfect matching like this. All three of them give the same graph. So the factor will be 3. Okay, so now let's, well, unfortunately, I don't have a luxury of these 6 blackboards today, so I sort of have to be a little more careful. Is this space? This one. So now let's look at the numbers there. So we have minus I to the power n3 plus n4 and so on. And I forgot also to remember when I was doing Gaussian integral last time, there was in the Gaussian integral there was a factor I to the n over 2, where n is small is the number of x's inside of the Gaussian integral. So this contributes as with the extra factor I to the number of these points. So in other words, I to the number of these points over 2, so it will be I to the number of h's. That's the extra factor that we will have there. And the number of edges in all these graphs will be, so it's the number of arcs. So we have a factor then I to the number of edges, and then h to the number 3 and 3 over 2 plus 4 and 4 over 2 plus 5 and 5 over 2 over 1 minus and 3 plus and 4 plus and so on. So let's look at these numbers. So in terms of the graph that is obtained in this way from a perfect matching, what is the meaning of this number? So we have n4 trivalent vertices, so the number of the endpoints of these vertices will be 1, 2, 3 from each vertex, and so 3 and 3 is the number of endpoints here. 4 and 4 is the number of endpoints here. So this number is the number of endpoints, but it's divided by 2. So when we'll divide, so the number of endpoints is the number of endpoints also of these upper arcs. If we will divide it by 2, we will get the number of arcs. So this is the number of edges. And, well, this is clear. This is the number of vertices. So what we have here is IH to the number of vertices minus the number of edges minus the number of vertices. So we have IH to the power minus the Euler characteristic of gamma. Okay, so we arranged these factors into including this one into IH to the power minus the Euler characteristic of gamma. Alright, so now we can write this sum over perfect matchings as this Gaussian prefactor and then sum over all graphs IH the minus the Euler characteristic of the graph. And then here we have the factor. This number, let me call it M gamma, divided over n3 3 factorial to the power n3, n3 factorial, 4 factorial to the power n4, n4 factorial, and so on, and then the weight of the graph itself. So now we have to understand what is the meaning of this number. So let's count the number of automorphisms, the number of mappings vertex to vertex, edge to edge, of the lower part of this graph. So which operations can we do which don't change this configuration? We can permute any pair of trivalent vertices. We can permute any pair of k-valent vertices. Nothing will change. So we have the S and 3, S and 4 acting trivially on these graphs. We also can permute edges inside of these stars of vertices. So this gives S3 to the power n3, S4 to the power n4, and so on. So this is the automorphism group of the lower part. So every graph we can represent like this. We can pull vertices down and we can arrange the rest, the edges, in terms of arcs. So this is the group of automorphisms of the lower part of the graph represented in this way. But then the full group of automorphisms of the graph, of course, it's this one divided by those automorphisms of the upper part which don't change the graph. And if you think about the size of this group, that's exactly n3 factorial, n4 factorial, and so on. 3 factorial to the n3, 4 factorial to the n4, divided by that number that's in the numerator, over m gamma. And so the size of this group, that's what we call the number of automorphisms of gamma. And so now we can write that this is equal to Gaussian factors, and then, well, I want to separate one from the rest of it, so 1 plus sum over non-empty graphs IH to the minus the Euler characteristic of gamma divided by the number of automorphisms of gamma, and then the weight of gamma. And now the weight of gamma you can compute just taking graph gamma, and so you take graph gamma, for example, here is graph gamma, you take apart this graph by cutting out stars of vertices and edges. So these are the edges, and then stars of vertices are separate. And then we put indices here, I, J, K, L, M, N. It's like in this model of statistical mechanics and graphs. So then you assign to this thing sum over all indices. In statistical mechanics, this would be states, and then product over edges. And then the weight of each edge is minus 1 ij, where I and j are corresponding states. Product of vertices, vi1, ik, and that's how you compute the weight of the graph without representing it as this diagram of perfect matching. So any questions about this part? If there are no questions, I suggest the exercise for everybody. So it's a 5 minutes exercise. Compute all diagrams of compute all contributions of first order. And just it's a nice exercise after which you'll remember this takes for a long time. So write explicitly contributions of order h. And I will just give an example of one contribution. So this is a graph whose Euler characteristic is the number of vertices is 2 minus the number of edges is 3, so it's minus 1. So IH to the minus the Euler characteristic is equal to IH, so that's one of the graphs of order 1. So first exercise, find all graphs of order 1. Find the size of the automorphism group for each graph, and find f of gamma in terms of b and v for each of these graphs. So, and the formula is for the contributions here. So you can start now. You have 5 minutes to do this problem, and then we will do it together.